We're going to practice the identities that we saw in 5.1, day 1. The directions for tonight's work or today's work will be to simplify, and answers may vary depending on what you choose to do. So let's just get started. We have cosine of theta times tangent of theta. And that's lovely, but perhaps it could be simpler. Shall we think about it for a minute? What do we have? Well, we don't have squares, so I'm not thinking about the Pythagorean identities. I could replace cosine theta with its reciprocal, but I'm thinking the best thing to do might be to replace tangent of theta with the quotient identity. So I'm going to keep cosine of theta, and I'm going to replace tangent of theta with the quotient sine of theta over cosine of theta. As soon as I do that, it becomes obvious that I can do some mathematics and simplify and end up with sine of theta. So in just 2 steps, I have turned cosine of theta times tangent of theta into sine of theta. And I don't think it's going to get any simpler than that. So I'm going to call myself done. Let's look at another one. Let's suppose the problem said sine of beta, and I do love beta, minus sine of beta times cosine squared of beta. And I was asked to simplify. First of all, even though trig is involved, the order of operations always trumps everything else. So please do not take sine of beta and think that the first thing we're going to do is subtract sine of beta and have 0 times cosine squared of beta, which would be 0. That would be wrong. The multiplication would have to come first. Okay, so what am I going to do? I'm not seeing myself using a Pythagorean identity right out of the gate. I could replace with reciprocals, but that would make my life a little more complicated. So I'm going to pull a different option. I'm going to do some algebra first. I have 2 terms. They both have sine of beta in common. So I'm going to factor out sine of beta. If I factor that out of the first term, I get a 1. If I factor that out of the second term, I get cosine squared beta. Now you might say that didn't make your life any easier, but based on experience, I know that it has, because 1 minus cosine squared beta is a piece of a Pythagorean identity. Let's go back and look for it. 1 minus cosine squared theta is sine squared theta. So 1 minus cosine squared beta must be sine squared beta. And sine beta times sine squared beta would be sine cubed of beta. And I don't think it's getting any simpler than that. Let's try another. Let's try cosecant theta divided by secant theta. And that's lovely. That is cosecant theta divided by secant theta. I'm going to temporarily make it look worse in the hopes of making it look better. So cosecant theta by the quotient identity, no, by the reciprocal identity, is 1 over sine theta. And secant theta by the reciprocal identity is 1 over cosine theta. I've created a complex fraction, so I'm going to rewrite this as a multiplication problem. 1 over sine theta times cosine theta over 1. And I can't cancel anything, but I can write this as cosine theta over sine theta. Wait a minute. Cosine theta over sine theta, that's cotangent of theta. So in several steps, none of which was too arduous, I replaced cosecant theta over secant theta is exactly the same as cotangent theta. Okay, notice that my work is flowing vertically, one step under the next. That is absolutely mandatory for our work with identities. So please get in the habit of putting your work vertically rather than streaming it horizontally. Let's try one more. 1 divided by tangent squared x plus 1. Well, I could replace tangent squared x with 1 over cotangent squared x. I could replace tangent squared x with sine squared x over cosine squared x. And all of those things might move me forward, but if I recognize tangent squared x plus 1 as part of a Pythagorean identity, I'm going to get to a simpler answer very quickly. So let's go back and look at our Pythagoreans. 1 plus tangent squared theta is the same as secant squared theta. 1 plus tangent squared theta is the same as secant squared theta. So let's look at what we've got. We've got tangent squared x plus 1. Well, that's the same as 1 plus tangent squared x. So this is 1 over secant squared x. And I could stop there, or I could recognize 1 over secant squared x. Well, 1 over secant is cosine. So 1 over secant squared would be cosine squared. And that's where I would stop. Okay. One last one before I let you go. We're going to do sine of beta times tangent of beta plus cosine of beta. Well, I have two terms, but they currently have nothing in common. So what am I going to do? I don't have squares, so I'm not thinking Pythagorean identity right now. I'm going to replace tangent beta with its quotient, sine beta over cosine beta. So sine beta times sine beta over cosine beta plus cosine beta. Okay. I do have students who occasionally think, well, I'll cancel the cosine betas. Please don't do that. We don't cancel an addition. And besides, order of operations would say the multiplication has to happen first. So I'm going to multiply. So I'm going to get sine squared beta over cosine beta plus cosine beta. That just looks terrible. So now I'm going to employ another strategy. I'm going to find a common denominator so I can add these fractions together. And you might be saying, how is she coming up with these things? Well, when there's nothing else you can do, resort to sort of the algebra that you know. So my common denominator would require that this one be multiplied by cosine beta over cosine beta, right? Okay. So then I've got my denominator, which is cosine beta, and my numerator now says sine squared beta plus cosine squared beta. Hey, hey, that looks like a piece of a Pythagorean identity. Sine squared beta plus cosine squared beta. Let's go take a look. It's getting farther and farther back. Cosine squared theta plus sine squared theta is 1. Oops, too far. Sine squared beta plus cosine squared beta, 1 over cosine beta. And wow, that looks better, but let's go for best. 1 over cosine beta would be secant beta. And that's where I would stop. Okay, now you're ready.